So what we'll do is, so I could get my hands on the last year's assignments and all. So we were supposed to discuss the last year's assignment. So what I'll do is I'll discuss those as well with the explanations and everything. So these are the kind of questions you will be getting in your exam only. So your exam is 22nd, right?
Yes, next Sunday.
Next Sunday. Okay, okay. So the kind of questions I'll discuss today is mostly you'll get similar kind of questions in the final exam as well. So MCQs and the numerical type questions. So I have covered mostly all from all the 4 weeks. So yeah, uh, let's get on. So in between, if we have any troubles, we can go back to the concepts and everything, and I'll tell you where basically you can find the concepts for these questions in the lectures as well. Okay. So yeah, this is the first question. So you can write the answers in the chat box also. So I'll put up the question, give you a minute or 2 minutes depending on the type of the question, and you can write the answers in the chat box, and we'll discuss it. Okay. So yeah, this is the first one. Yeah, only you, if you are only here, so you can also like unmute and tell me your answers as well.
Okay, I think option C because it contains x square term,
Okay. Okay.
so it is non-linear.
Option D you said, or C?
C, C.
Okay. Okay, but no. The correct answer is option A actually. So the order of the ODE is the highest derivative in the equation. So a first order ODE will only have dx dt. It will not have dx to dt2. So the order is the highest derivative. Order of an ODE is of the highest derivative of the equation. So if it is a first order non-linear ODE, it's the order is 1, so only dx dt will be there, not dx to dt2. So it's from the first two. And in a linear ODE, the dependent variable and its derivative should have the power of 1, and there should be no product of the dependent variable with the derivative. So that's why a plus bx, this is a linear ODE, because x has the power of 1 and it is not multiplied by any other kind of variable. And so this is a linear first order ODE, option B. And option A is actually a non-linear first order ODE. First order because your dx dt is the highest derivative is 1, and also x is non-linearly dependent on dx dt, but and it is not also multiplied by anything. So basically this is a first order because x is linearly dependent. This is not, because x is not linearly dependent. So the option will be A. Okay. I hope that explains it. Okay. Let's move on to the next one. So
Option First one, the rate of
Yeah,
the reaction is equal to K into X.
yeah, that's correct. Oh, yeah. So there can be, I think the
The
answer.
question is wrong.
Yeah.
Which one is wrong?
Okay, yeah.
Okay.
The question is which one of them is wrong. Actually, yeah. So first one is actually you can represent this as the rate of the equation. So there can be many like representation of the rate of the equation that can be on the basis of the substrates, that can be on the basis of the products as well. So this is the first one is a valid rate of the reaction. The second one is actually also a valid rate of reaction, because in terms of dz dt, so one third is to balance out the stoichiometry, and dt is getting formed, so that the positive sign is there. And for the third one, this would have been the rate of the reaction had this gotten a negative sign. If this were minus dy dt, this would have been a rate of reaction, but only dy dt will not be a rate of reaction because y is getting used up, so there will be a negative sign. Again, d 1 by 2 dx dt is can be the rate of the reaction, because there is 2x, so 1 by 2 to balance the stoichiometry, and negative to imply that it is in the substrate, it's getting used up. So the correct option is option number 3, because it has asked which of the following statement is wrong. So yeah. Okay, moving on. Sorry. Okay, let's try to solve it. Okay, so the sorry. So the question says this is the rate. This is the dx/dt equation, which is the model, OD model of spread of disease, which is like quite simple. And here the R is given, and R naught is given as 10%, and it has asked what will be the size of the infected population on the 100 day. Okay, so let's try to solve. Okay, so dx dt equal to r into 1 minus x. So r is given as 1, x naught is also given, x naught is given as 10%, so it's basically 0.1. So x naught equal to 0.1. Now you try to integrate this. So if you put r equal to 1 here, so this becomes dx dt by 1 minus x. Oh, there's one x here, I think. Right? Yeah, there's one x here, right? Instead of x. So x into 1 minus x. Okay. 1 minus x into x. If you integrate this, say x naught to x, and on the other hand there is time dt, you there's the r here as well, So 0 to t. Yeah. So this becomes a negative log. You can just do 1 minus x plus x on the numerator and split this up. I'll not go into the integrate calculations, but comes out to be the log 1. So log of 1 minus x by x, this comes out like this, and it goes from x naught to x equal to rt. Now if you take so basically if you put x and x naught here, and it will be like, if you take the negative inside, so log of 1 minus x naught by 1 minus x into x by x naught. Yeah, this is what it, if you take the negative inside, now it equal to rt. Now r equal to 1, and you take anti-log of this, so this becomes 1 minus x naught by 1 minus x naught into x equal to the power minus t. Then you put the values, so you have x naught equal to 0.1, r equal to r I have already put here, so your x will become, I'm just writing the equation here, I have already solved this, so yeah, if you rearrange the terms with x on one side and x naught on the other, so it becomes something like this, by x naught e to the power minus t. Yeah, now you have, the question has been asked, what would be the size of the infected population on the 100th death. So your your t here equal to 100, so you put t equal to 100, you put x naught equal to 0.1 here, so this becomes something like this, x equal to 1 by 1 plus this 1 minus 0.1, this is like 0.9 by 0.1 e to the power minus 100. If you calculate this value in a calculator, so this is basically, this becomes 9, so 1 plus 9 e to the power minus 100 of the reciprocal of this comes out to be approximately this comes out approximately around like 0.9999, so equal to it's actually equal to 1. So if you do this calculation, so the answer is 0.99 or 1. So it's quite simple. This is the equation, you integrate it, put the values in, your you'll get the answer. So yeah, the answer is around that 0.9 or 1 range. Okay, it's more.
Calculators will be available in the exam, right? Scientific calculators.
I'm not sure about that. You need to clarify with the NPTEL people. I'm not aware of the rules of the exam, like in the sense what is allowed in the examination hall or not. I'm not
Okay.
sure. If these kind of questions will come where you need to like calculate the value of E or something, either the value, that particular value will be given, or you'll be allowed the calculator. So don't worry about that.
Okay. And the questions will be in MCQ, right?
Yeah, MCQ and this kind of like
Describe.
numerical uh, answers like this.
Oh, okay.
Short numerical answers, but that can be in the form of an MCQ as well. So this can be in form of an MCQ as well, right? So
Mm-mm.
you give
Yes.
4 options. So yeah.
Okay.
So if you want to like revisit the concepts of this question, these are like in the lecture 4 of the first week. So I just want to let you know if you want to revisit the part.
The first one, a parameter in an ODE changes with the time.
Yeah, that's true. Actually, that is false. So that's the question that has been asked. So which of the statement is false? Yeah, a parameter does not change with time. So that's the constant there. So in the previous case, it was r, which was 1. So yeah, so that does not change with time. Dependent variable might change with time because it's a dependent variable and time is the independent one. It it can have only one independent variable, and PD can have more than one independent variable is also. So there is no relationship between having a PD or a OD and the number of independent variables. So yeah, so the correct option is the first one.
Option C.
Yeah, yeah, it's correct. So there are a couple of things to notice. So if you just see the four options and just see the the death rate, how it has been modeled. So death will be all obviously minus RP because in the first one it is inversely proportional, which is not possible. Death cannot be inversely proportional because then it will increase the population. On the other hand, this does not account for the second option does not account for death also, and the fourth option account for death in a positive manner. So by just looking at the death equation, death term, you can understand ki the third equation is the correct one. Also, this is the first part is a logistic growth equation. So this is where the population increases, and the minus RP denotes the death and the decrease in the population. So yeah, it's quite straightforward. Okay.
Which one I couldn't. I think option A or
Okay.
C.
Okay, I'll tell you the logic. So, if you see the values of x are at t equal to 1.01, and this is sorry, yeah, at t equal to 1.01, the values are 0.102 and 0.101. So the difference in x, so delta x, how you calculate, is basically the difference in the two values. So it's 0.001 if you just subtract these two, and the time step here is basically point sorry, yeah, so the time step here is 0.01, and the delta x here is 0.001, which is less than the time step taken. So the acceptable error rate is in numerical methods, how we defined is basically uh, uh, the the time step that you are taking in, the change in x that you are taking is the amount of error that is possible in change in x, change in y. So in the x-axis, the amount of change that you are taking, that is the maximum amount of error that is allowed between the two values of x. So in the difference between the two values of x, it's 0.001, which is lesser than the time step taken, which is 0.01, which is which basically means your time step is small enough, and so you should accept the result obtained by the better method, that is the fifth order Rangi-Kutta step. So the third option is actually the correct option. So the logic behind it, I am sure you understood. Like the difference in the values of the x should be lesser than the time step taken. Okay, so that is how you'd say like which is the acceptable amount of error here. So which is less than 0.001. So the acceptable amount of error is 0.01, which is your delta t, but your values of x are different in 0.001, which is lesser. So that is acceptable.
So can we accept a fourth order?
Sorry?
A fourth order Rangi-Kutta method can we accept?
Yeah, yeah. Basically, fifth order is giving you a better, like basically result than the fourth order step, right? So you can accept the
Yes,
fourth
yes. Oh,
order as well. So which is the best option actually you are choosing?
okay.
Okay. Okay, this we need to calculate, so let's do it together here. Okay. So the equation is, so I just quickly show you the problem. So you are given an ODE, this is your ODE, and you are asked to use Euler method to calculate the value of x at t equal to 0.2, and your t minimum is basically at t equal to 0, your x is given, and your time increment is given as 0.1. So let's try to solve this using Euler method. So dx dt, yeah, dx dt is given as 1 minus x square. So basically you have t, you have delta t. So because you'll be you'll have t and delta t, you'll increment t by a small amount. Your value of x will change as well. Dx dt you need to calculate from here, and dx dt into delta t. So basically let me write it like this. Yeah. So you have dx dt here. You have, if you remember the Euler equation, so basically I'll write the equation here first, how we calculate. I hope you remember. So basically your x of t plus delta t is actually I have it here somewhere. Let me okay, let it be. So yeah, so this is x of t, and yeah, x of t plus dx dt into delta t. The equation is basically, if you take x of t to this side, so dx dt is defined of x plus x of t plus delta t minus xt by delta t. So if you rearrange, your x of t plus delta t is equal to xt plus dx dt into delta t. So this is your Euler's equation, this is how you increase small amount of delta t, and that's how you'll get the value of x and dx dt. So if you start, so we'll have the following parameters. So we have t here, you have x, so let's write it like t and delta t here. Then you have x of t, what is the value of x of t. Then you have what is the value of dx dt. Then you have what is the value of dx dt into delta t. These are the like 1, 2, 3, 4, 5 things you need, and ultimately you can calculate this x of t of delta t from this equation. So if you okay, so you start with t equal to 0, delta t equal to 0.1. Okay, so your x is given here, so your x at t equal to 0 is given as 0.1. Okay, and delta t is also given as 0.1, so we are taking delta t as 0.1, so x will also be 0.1. Now if you calculate dx dt is basically 1 minus x square, so 1 minus 0.1 whole square is equal to, this is basically
First, we have to differentiate that equation, 1 minus x square. Then only we can substitute the value.
sorry,
First, we have to differentiate that thing. Means
why your dx dt is defined like this, na, 1 minus x square.
okay.
You don't need to differentiate, so I put the square sign like this. Okay, yeah, so it's 1 minus 0.1 square, so 1 minus 0.1 is basically 0.99, right? Then dx dt into delta t will be 0.99 into delta t is 0.1 equal to 0.099. Now if you take xt plus dx dt into delta t, if you add this up, so 0.1 and 0.099, 0.1 plus 0.099, right? Now let's try the second step. So this is now 0.1, then sorry, so we started off here, so there was no oh no, I'm correct. Okay, so 0.1, next t is 0.1 because your delta t is 0.1, so t is 0.1 and your delta t is 0.1 here again. Now xt is this one at t equal to 0.1, 0.199. You take this again, 0.199 square, like this. This comes out to be, I think, if I remember, yeah, this comes out to be 0.9603, something like this. So many decimal places are not required, but anyway. So yeah, and this you multiply into 0.1 like this here again, so this becomes another 0 in there, 0.09603. Let's put 3 as well, and here it becomes 0.199. So your x is 0.199 plus this thing 0.09603. So this becomes, if I remember correctly, 0.295. Yeah. So now your x is at 0.2, your delta t is again 0.1. Now your t is 0.2, delta t is 0.1. Now your x value is 0.295. So this is what the question is asked actually. what is the value of x at equal to 0.2? The answer is 0.295. Right. I hope you are okay with the method as well. So it's simple. You just need to like calculate each and every expression and put it in the next step. So yeah, the answer is option, I think option 2. Yeah, option 2 is the answer. Okay. So, so let's move on to the next one.
Option C, either method is an exact method.
Yeah, that's true because it's a numerical method. It's based on approximations. It's not an exact method of solving it. So yeah, that's correct. Okay, let's move on to the next.
Uh, C or
Sorry, I did not hear.
option C or D.
Okay. Uh, the option is option C. So I see you have some confusion. So let me like write it here. Okay. So the equation is 3 molecules of X react with 2 molecules of Y to generate 1 molecule of Z. So the reaction is 3X plus 2Y reversibly giving 1 molecule of Z. Right. So if your forward reaction is K1 and your reverse reaction is K2, so if you try to see dz dt will be so x is sorry z is getting generated from x and y, and they have coefficient 3 and 2. So this will be x to the power 3, y to the power 2, and into k1. So this is the forward rate. So z is getting created. Now if you want to look at the term and in which z is getting used up, which is the backward reaction, will be minus k2 into z. So it is basically the third option, this one, right? 3 molecules of X forming with 2 molecules of Y forming 1 molecule of Z. So in the forward reaction, Z is getting formed. So K1 into X to the power 3 and Y to the power 2, and Z is getting used up in the backward reaction, which is minus K2, and it is dependent on Z. So the third is the correct option. Okay. Yeah.
It should be homogeneous.
Yeah, that's correct. So that is a kind of that basically uh, two major assumptions are there for ODE based modeling majorly. So one is this system is homogeneous, another that the system is very large. So when the system is not homogeneous, the concentration or the number of component varies with spatial position. We do not use actually ODs, we use PDs. and basically the rest of the options are wrong actually. So yeah, okay, let's try some JSIM as well. So these kind, if from JSIM you'll find this kind of questions only. So it will not ask you to simulate on anything. You'll be given a code like this, and you'll be asked to say where there is a mistake or which is telling what. So like this, the questions will be like this. Not you'll be not asked to simulate or anything.
I think the initial value is t dot minimum.
Yeah, that's
Here
correct.
they mention t dot maximum.
Yeah, so the here the question is identify the line of the code. So your answer will be line number 9, which basically you have to define t equal to t minimum and what is the value of x and y at t minimum at the start basically. So it's actually the opposite that is provided. So it's wrong here. So yeah, the answer is line number 9, where you have to provide t minimum, not maximum. Okay, so yeah.
Can you provide the calculations?
Yeah. Okay. Let's do it. So your equation is dxdt equal to k1s minus k2x, right? So this is your equation, dxdt equal to k1s minus k2x. Now the values of k1, k2 and s are given. Yeah. So k1 equal to 2, k2 equal to 1 and s equal to 1. So let's go here. So this becomes, this is basically 2, k1 is 2 and s is 1, and this is 1, so 2 minus x. So you can directly solve this analytically. So dx dt equal to 2 minus x. Right? Now you put dx by 2 minus x equal to dt. Now you integrate x naught to x and you integrate here 0 to t. Right? So this becomes negative log of 2 minus x naught to x equal to t. Now you take log and basically put the value of x naught here. So log of 2 minus x by, since there is a negative, it will be flipped. So now this is what it becomes, equal to minus t. Now your x naught is given here. So yeah, so your basically t at time t equal to t is given as 3600, and your x naught is given as basically yeah, your x naught is given as 0. So at t equal to t 0, your x naught is also given as 0. So x naught equal to 0 and t equal to 3600. So this will become, so let's take anti-log. So if you take anti-log and solve this will become 2 minus x. So x minus 2 will be on this side, and if you take anti-log here, so yeah, 2 minus x naught e to the power minus t. So you put x naught equal to 0 and t equal to 3600. So x will be 2 minus 0 into e to the power minus 3600. So 2 minus 2 e to the power minus 3600. So this is like, this is actually very small, this part, so you can consider this as 0 only. So this goes to, I think, 7 or 8 places of decimal, so this is approximately equal to 2. Right? So your value of x is basically when t tends to infinity, which is like basically 3600, or if you take t more than that as well, so your basically e to the power minus, and it will increase, so this portion will further go to 0, so x will be approximately equal to 2. Let's check the answer. Yeah, so x will be equal to 2. Okay, so I hope that was clear. I'll give you a couple of minutes, then I'll solve it.
Four comma four.
I have to check myself. Just a second. Try to solve this. Okay. So your dx dt. So your dx dt equal to 1 is x minus 4, another another dy dt, sorry, is how much? X square minus y square. So, yeah. Now, at steady state dx dt equal to dy dt equal to 0, right? So you put dx dt equal to 0, x equal to 4, dy dt equal to 0, x square minus y square uh, equal to 0. So x square equal to y square. So x equal to plus minus y, or y equal to plus minus x. So yeah, if you are asked to, I think you are asked to give the positive state values, right? Yeah. So the answer will be x equal to 4 and y equal to 4. I think that is the answer. Yeah. So y equal to 4. Okay. Let's move on. Just switch off my camera for a second. Should I try solving it now?
Yes. I unstable point is 1,
Okay.
and the numerical value is zero 0.9 into 1.
Okay. Okay. Unstable is 1 is correct. And what is the sign?
minus 0.09.
Okay. Okay. Strides here. Okay. So your equation is dx dt equal to x square into x square minus 1. So dx dt equal to x square into x square minus 1. So for steady states, dx dt equal to 0, which means x square into x square minus 1 equal to 0. So you have x equal to plus minus 1 or 0. So there are three values of steady states. So you have to check which of them are steady, which of them are stable and unstable. So let's start with x equal to minus 1. So if you remember, we did with tables. So we'll check that the value of x a little bit higher than that value and a little bit lower than that value. So for x equal to minus 1, we'll check for dx dt, and we'll put an arrow sign like if it is converging or diverging. So okay, x equal to minus 1, dx dt is obviously 0. So and there is no arrow here. So let's put it like this, sidewise. Now if you take a value slightly higher than x equal to minus 1, so x equal to minus 0.9. So careful, remember there is a negative sign. So x equal to minus 0.9 is greater than x equal to minus 1. Okay, so be careful about that negative sign. So if you take x equal to minus 0.9, actually this becomes, I have calculated some here. Yeah, so this becomes actually, if you put x equal to minus 0.9 in this equation, dx dt will be basically 0.9 whole square into 0.9 square minus 1. So this approximately comes up to minus 0.15. Okay, you can do the calculation here. So minus 0.15, and since it's a negative, it'll converge towards the steady state. Now let's take a value of x slightly lower than x equal to minus 1. So x equal to minus 1.1. So here also, like sorry, there is a negative here. Yeah. But this will kind of go off because there is a square. So minus 1.1 whole square into minus 1.1 whole square minus 1. So this actually comes out to be a positive because you see 1.1 is greater than 1. So this will be a positive. This is approximately 0.25. Okay, so this is a positive one, so 0.25 here. So the arrow is converging. So x equal to minus 1 is a stable steady state. Okay, now let's look at x equal to 0. So at x, same thing. So I'm just drawing the same table here. So at x equal to 0, your dx dt is 0 because you put an x equal to 0, this becomes 0. So dx dt is 0, and this is this. Now if you take a value slightly higher than 0, so x equal to 0.1, and you put it here. So 0.1 whole square into 0.1 whole square minus 1. So this will also come out to be negative, and this is approximately minus 0.009 if I'm correct. We will do from here, one from here, minus 0.009. So 0.009, this will be a negative, right? So negative means it is converging towards the steady state. Now if you take a value slightly lower, so minus 0.1. So this actually, if you take negative here, this just yeah, this just gives you the same value because minus 0.1 and 0.1, the square of will be the same, so this will give you the same value, 0.009. So this is also converging. This is actually diverging since it's negative. So this is actually a semi-stable steady state because on one side it is converging and one side it is diverging. Right? So this is semi-stable. Now you do the same for x equal to plus 1. So x equal to 1. So at x equal to 1, the value of this is basically 0 because this 1 minus 1 is 0. So value of 0. Now you take a value slightly higher than 1, x equal to 1.1. We have already calculated x equal to 1.1 is this. Negative sign does not matter because this will square off, so it will be 0.25. So it's a positive 1, so it's going up. And if you take a slightly lower value, 0.9, this also we have calculated with a negative sign, but the value will be same because there is a square. So minus 0.15. So this will diverge. So this is actually an unstable steady state. Right. So at x equal to minus 1, you have a stable steady state. At x equal to 0, you have a semi-stable steady state because one side converging, other side diverging. And x equal to plus 1, you have an unstable steady state. Right. So the question was the numerical value of x for that unstable steady state. So for unstable, x equal to 1. So that is the answer. Okay. Yeah. So like I'll suggest to practice this kind of sums because most probably one or two sums will be like this in the exam also. So practice doing this table and getting the steady state and how the steady state is behaving, stable, unstable, semi-stable. So yeah. Okay.
Can you do the calculations?
Yeah. So your equation is dx dt equal to x into 1 minus x, right? Now the question is, what is the direction of the arrow in the direction field for the following ODE? So first, what is the direction field of at a particular point? The direction field is nothing but the slope of the OD at that particular point, right? So what it's basically asking you is how is the slope at that particular point of the OD at like x equal to 0.5 and t equal to 8? How does the slope of the OD look? This is what it is asking. What is the direction of the arrow in the direction field of the ODE at this point is basically what is the slope of that ODE at this point, right? So you just need to find out what is the slope of x and t at that point. So the slope is, sorry, the slope is given by dx dt. So you have to find the value of uh, dx dt at x equal to 0.5 and t equal to 8. It's quite simple. So t x equal to, let me write it down here, x equal to 0.5, t equal to whatever will be the value of t, because t equal to 8. Yeah, it's not going to be important because this equation does not have t in it, so whatever be the value of t, it does not matter. The slope only depends on x. So your dx dt will be 0.5 into 1 minus 0.5. This is like 0.5 into 0.5 equal to 0.25. So this is a positive slope, right? So the and this is like less than 90 degrees, so the arrow will be something like this. So if what it means is basically if you plot x versus t at x equal to 0.5 here, the slope will be something like this. 0.25, if you have a line with a 0.25 slope, it will be something like this. Like it will be an acute angle, but it will be in a positive direction because your slope is positive. So the direction field will be given by, I think, option number C. Let me check. Yeah, option number C. It's actually nothing but the slope of the OD at that particular point. T is given, but there is no T in the equation, so the slope does not depend on T. Only you need the value of x for the slope. Okay. Moving on.
Uh, two two possible steady states. One is 1 comma 1, 0 comma 0.
Yeah. So your null lines are your x and y null lines are meeting twice. So that means you'll have two possible steady states, and yeah. So this is so basically this is one steady state and this is one steady state. So 0 comma 0 and 1 comma 1. That's correct. The answer is two possible steady states. Okay.
is 2.
Yeah.
It is not clear in the graph.
Yeah, it's actually two. The reason is quite simple. So in two, what you'll find is basically from one side, it is converging. So if you just consider this two steady state, so on from the left here it is converging, from the right here is also converging, but from the top and bottom it is actually diverging. So from one side it is converging, from one side it is diverging. So this is a saddle. On the other hand, these two all are converging, so these are stable steady state, so these are sinks, right? This is a sink, this is a sink, but this is a saddle because from one side it is converging, from other side it is diverging. So yeah, the answer is correct. uh, Point 2 is the saddle state. Yeah.
Graph is very small.
Oh, you can't see?
I mean, the values. Now it's okay.
Now it's okay.
Okay. Option C. Uh,
Option C. Let's check it.
I think option A.
Let me check it. I also have to check. So, let me write down the equations here. Sorry. Okay, so dx dt equal to 1 minus kxy by 2 and y. Okay. So dx dt equal to 1 minus x into y by 2, and dy dt is equal to y minus xy, right? I hope I've written correctly. Yeah. Okay. Now you're asked to find the null line of x and y both. So for x, dx dt equal to 0. So this becomes x into y by 2 equal to 1. So if you put this as 0, your xy equal to 2, or x is 2 by y, right? Now for the second one, y is y minus xy. So this is equal to 0, so y equal to xy. This becomes y equal to x y. So from here either y equal to 0 and x equal to 1 from this equation. So you have three equations primarily. So you have one is this, two is this, three is this. So this will be a hyperbola. So xy equal to constant is a hyperbola. And it's a positive hyperbola. And y equal to 0 is the x-axis, and x equal to 1 is parallel to the y-axis, right? So let's check the answers here. Okay. Okay, so C.
C. Ah,
Sorry.
C is the answer, I think.
No, actually, so C is not the answer because just look at the equations here. Y equal to 0, which is the x-axis, right? So in C, x-axis is not marked. This is the x-axis. It's marked as x equal to 1. So this is not correct. This A is correct because this is the x-axis. This line is vertical line is the line corresponding to x equal to 1, and this is the hyperbola corresponding to y equal to 2 by x or x equal to 2 by y, right? So from x null line, this is the first one is your x null line. So from x null line, x equal to 2 by y. So this is this blue line from your x null line. From your y null line, you have y equal to 0 and x equal to 1. So y equal to 0 is the x-axis and x equal to 1 is parallel to y-axis, right? So this is the x-axis that has been marked, and x equal to 1 is parallel to the y-axis. This is the one that has been marked. So the correct option is option A, not option C. In option C, it's exactly same, but just instead of y equal to 0, y equal to 1 is marked. This is y equal to 1. This is not y equal to 0. Y equal to 0 is here, x-axis, right? So option A is the correct one. Understood?
Yes.
Okay.
Option C.
Yeah, the correct answer is option C. So basically, any change in the parameter of value would change the numerical value of the possible steady states. That is true, right? But that is not bifurcation. What is bifurcation? In bifurcation, a change in the numerical value of the parameter, which is the bifurcation parameter, will cause a change in the number of steady states or the stability of the steady states or both. So option number 3 is correct. Okay, so yeah, let's move on.
Can you do
Hello? Sorry, I couldn't hear you. Yeah?
can you do the calculations?
Yeah. Okay. So, okay. Your equation is dx dt equal to r into 1 minus x by k into x minus t. Okay. Your r is 10, k is 10. Okay. So, your dx dt is r into 1 minus x by k into x minus t equal to 0. So at steady state, obviously this is 0, so I'm directly putting this equal to 0. So this becomes 0. So from this you can calculate. So we need to rearrange a bit. So r x k minus r x square minus kd equal to 0. Now rearrange rx square minus rxk minus kd equal to 0. Now from here you have to use the quadratic formula. So for the steady state value, x equal to minus, so I'm just writing the formula here, minus b plus minus root over b square minus 4ac by 2a. This is the quadratic
Here
formula.
it is plus KD.
Yeah, sorry, this will be plus. Sorry, yeah, okay. So the value of b here is basically minus rk. So minus b is rk plus minus b square r square k square minus 4. A is basically r and c is k. So 4 r k, sorry, c is kd, not k, c is kd. So 4 r kd, right, by 2a. A is r, so 2r. So here d is your bifurcation parameter, right? So if you see, if see the one that is inside the square root. So when r square, sorry, let me erase this. So the roots will be imaginary. Yeah, the roots will be imaginary if this is negative. If this is negative, meaning 4 rkd will be greater than r square k square. Or if you just, if you consider r and k to be non-zero, you can just cancel this out. So this will become 4d is greater than rk, which is d greater than rk by 4, and at this point x is imaginary. So when when this conditions hold, sorry, this is k, when this condition holds, x has no real steady states. X has no real steady state, right? Now as k and r is given here, I think, yeah, k and r is given as 10. So k equal to r equal to 10. Then the critical point beyond which there is a bifurcation. So this is a greater than equation. So d is greater than rk by 4. Under this condition, x is imaginary. But when d equal to rk by 4, since it is, this condition is not included here, so this is a real steady state, right? Not real steady state. This you can call actually the critical value of the steady state, beyond which the steady state goes from real to imaginary. So this is basically the critical value. So beyond this, when d becomes greater than this rk by 4, it becomes imaginary. So the critical point is rk by 4, on the left of which it is real. When it is equal to rk by 4 or lesser than rk by 4, it is real. When it is greater than rk by 4, it is imaginary. So the critical point is d equal to rk by 4. So and r and k is given, you can just calculate d from there. So 10 into 10 by 4 is equal to 25. So your critical value of d is basically 25, beyond which the basically the steady state is imaginary. Okay, so I hope this is the answer. Yeah, 25 is the answer. So that's the critical value of d. Okay. Let's move forward to the next one.
Can you explain what is incoherent forward loop or something?
Okay. So feed forward is basically first understand feed forward loop, then we'll understand what is incoherent. So feed forward is where information from the input node to the output node reaches to through two paths or more than one path. So all of them. So for example, take A. So information from A, from this node to this node, is reaching through here, and also so for example, let's take the other node. So this node to this node, information is reaching directly from here, and also information is reaching from here as well. So feed forward is when information from the input node to the output node reaches through two different paths. And in incoherent feed forward loop, these two paths have opposite signs. So these two paths should have opposite signs in case of incoherent feed forward loop. So this motif A here is a coherent feed forward loop, and D here is as well a coherent feed forward loop, because these two negatives make a positive. So ultimately this is a positive only. So this is positive, this is positive. Here also this is positive, this is positive, and this is positive as well. So these both are coherent feed forward loops because they have the same direction. And B is basically a positive feed forward motive. So there is no, like, this is basically a feedback loop, right? So information is starting from here, it is going back to here. So this is a feedback motive. This is not a feed forward motive. A and D are feed forward motive. C is also a feed forward motive, but A and D are coherent feed forward motives because the signs of the arrows are same. And in this case it's different, but two negatives here is basically what it is meaning is a positive till this node. So these two are coherent feed forward loops. B is a feedback loop. C is basically an incoherent feed forward loop, because here also information is reaching from this node to this node, but this basically the paths here are opposite in nature, have opposite signs. So this C is an incoherent feed forward loop. A and D are coherent feed forward loops. Okay, so option will be answer C.
Okay.
Let's move on.
Option C, all the steps in the enzymic reaction are reversible.
No, not actually. So you can have Michaelis-Menten for like, so it is possible कि you'll have a two-step reaction. In one step it is reversible, the other step it is not reversible. So that is not an assumption for Michaelis-Menten. What Michaelis-Menten assumes is basically the enzyme substrate complex, the ES value. So I'll just write it here. So this complex, ES complex, is in equilibrium or steady state. This is what the main assumption of Michaelis-Menten model is. So we assume that the enzyme substrate complex is in a steady state, but that is possible only when there is a continuous production and breakdown of the complex. So because this is an intermediary complex, so your equation is E plus S. This gives rise, this is reversible, gives rise to ES, and this breaks down to give you E plus P. This is actually not reversible, as you see. This is a forward reaction. This is not reversible. This equation is reversible. This is not. So what it assumes is this entity is in a steady state. This will only be in a steady state where there is a continuous production and breakdown of this complex, because this is getting broken down and this is also getting produced. So if that rate is equal, the rate of production and the rate of degradation is equal, then only it will be in a steady state. Now for this to be steady state, like the concentration of enzyme won't change, because that is continuous to throughout the reaction. So but the substrate will get used up. Okay, so to achieve a continuous formation of this enzyme substrate complex, what you have to do is the concentration of the substrate must be much higher than the concentration of the enzyme. So actually the first option, this is what basically is the assumption, that this amount of substrate is much greater than the amount of enzymes. So what happens is basically in applications, when you look in for different say for example you are applying this in some sort of like enzyme complex reaction, so what you assume is the amount of substrate is continuous. There is no dearth of the substrate. The enzyme might be limited, but the amount of substrate that is unlimited, at least much greater than the enzyme. So actually the first option is the correct option, right? So and this is not correct, because this reaction is not reversible, right? So option number one
Okay.
is the correct option. Yeah. Yeah. Okay.
Is option B. And before that, can you explain what is Hill constant and their coefficients?
Okay. I think I have it in a slide here, so let me check once. Yeah. And yeah. Yeah. So basically, what is the Hill function? So we have the ligand and basically the substrate binding equation for simple enzymes which we follow the Michaelis-Menten equation. So they exhibit a hyperbolic reaction velocity curve. But many of these enzymes, such as regulatory enzymes or other enzymes, they are basically referred to as oligomers, and they do not follow, because they'll have multiple units, so they do not follow Michaelis-Menten equation. Their reaction velocity is not hyperbolic, it is sigmoidal. So it is like this, sigmoidal. So this is the Hill equation, which tells you basically the theta is basically the fraction of the receptor protein concentration that is bound to a ligand. So this is in context of a ligand receptor binding situation. So your theta, which is the fraction of the receptor protein concentration that is bound to the ligand, that is given by, where L is your ligand concentration, Kd is your dissociation constant in which the ligand and receptor dissociate, and your Ka is Kd is the apparent dissociation constant, K is the normal dissociation constant, and your N here, so L to the power n, Kd plus L to the power n, your N here is what determines is the Hill coefficient, which describes the cooperativity. If it is a cooperative binding, N is greater than 1, and if it is non-cooperative binding, N is less than 1. So the Hill coefficient provides a way to quantify the degree of interaction between binding ligands. The higher the value of the Hill coefficient, the higher is the affinity of the complex to be together. So you are asked here, what is the difference in the Hill coefficient between these two curves? So what the Hill coefficient actually determines is basically in terms of the reaction velocity of the curve. Basically Hill constant decides the half saturation value. So this is the full saturation is like at y equal to 1. So this is the full saturated value. The half saturation value is determined directly by the Hill constant. It's the same as the Km value in the Michaelis-Menten equation. So it depends on the half concentration, basically saturation point. So in this curve, the dotted curve reaches half saturation, which is like y equal to 0.5 here. The dotted curve reaches the half saturation at a lower value of x. So the x value is lower here than the like non-dotted curve, that is the normal line curve. So here the x is much greater compared to here. So the Hill constant for the dotted curve must be smaller than that of the solid curve, right? So if your Hill constant is greater, the half saturation value will be reached at a lower basically at a lower time point. So if your half saturation value is reaches at a lower value of x, then the Hill coefficient will be lower. If the half saturation value reaches at a higher value of x, the Hill coefficient is higher. So in the answer here will be the first one. The Hill constant for the dotted curve is smaller than that of the solid curve. So basically it is determined by y equal to 0.5. At which value of x does y equal to 0.5 is reached? If it is a greater value of x, then the Hill constant will be greater. If it is at a lower value of x, the Hill constant will be lower. So the option A is correct one. The Hill constant for the dotted curve is smaller than that of the solid curve. Okay. Sorry. Yeah. Okay. So if you want to know more about Hill function, so these are the two things that we discussed. Hill function, what is the Hill function, and how does it relate to the Waddington's landscape. So we discussed these two things, but if you want to learn more about Hill functions, I think the Wikipedia page is actually pretty good. I was going through the Hill function here. So here actually they have explained it pretty well. what is what and how do everything's change and everything. So there's one example as well as for tissue response. So you can take a look at this page if you are facing any difficulties. This explains very well. Okay, the Wikipedia page is pretty good for this actually. So yeah, okay, let's move on.
Option B.
Option, sorry, B or D?
B. B.
B for Bombay.
Ah,
Yeah,
second.
yeah. Uh, you're correct. So the reason is, so the question says that the gene is expressed only in the presence of both the signals, right? So what it means is when either of S1 or S2 is 0, not both, even if one of them is 0, the rate of production must be 0. So all these equations, the first term is the rate of production. So this part is the rate of production, and minus K3M in all is the rate of degradation, right? So only in the second option, if you see here, if S1 S2 as either of them are 0, the rate of production becomes fully 0. In all of the rest of them, if either of S1 or S2 is 0 but the other is non-zero, the rate of production does not become 0. For example, in this one, if S1 equal to 0, doesn't matter if S1 S2 is like if it is a positive or negative, this production term will be non-zero. Only in case of this thing, this like option, since both of them are multiplied, either of S1 or S2 equal to 0 would bring the production term to be 0. So option B is the correct option. Correct. Okay, let's try to solve this. Okay, so the question is that the ligand L binds to the receptor R to form a complex C1. C1 is autophosphorylated to C2, and the dynamics is shown here. So this is the one, and throughout the process, the total number of receptors is constant, which is basically these three R, C1 and C2. Total number of ligand is much higher than the total number of receptors. We have to create an ODE based model. The ODEs are not shown here. Which of this is basically the null line of C1? So first we need to find the model and then we'll find the null line. Okay, so let's try to do it. So the question is here. Okay, so L binds with R. This is the equation. This is the reversible equation. K1 is the forward, K2 is the backward, and it forms C1, and then from C1 it dissociates into to C2, and then C2 is again forming R, right? So if we write this equation here, so if we write in terms of dc1 dt, right? So on, like before that, r total is given as r plus c1 plus c2. So this is constant, rt is constant. Okay, so in terms of c1, let's go back here. Okay, in terms of c1, it is forming lr, it is getting formed from lr. So c1 is getting formed from l and r with k1. So let's write this down here. So k1 into lr, right? Now this is getting used up by c2 with rate k3. So there will be a negative K3C1, and from this reversible reaction C1 is also getting used up by K2. So there will be another negative K2C2, right? K2, sorry, K2C1, because it is getting used up by K2. Okay, so this is the equation for C1. Note that L is much greater than RT, it is given. So L, the total number of ligand is much higher than the total number of receptors. So RT is the number of receptors and ligand is L. So L is much greater than RT. Okay, that is the condition that is given as well. So L is greater than RT. Okay, and this is your equation for dc1 dt. Now for dc2 dt, let's try to do the same. So okay, so this is dependent on basically dc2 dt is getting formed from c2 is getting formed from c1 with k3, and it is c2 is getting used up to form to form r with the rate k2. So positive from k3, negative from k2, right? So dc2 dt will be k3 c1 minus k2 c2, right? Now in the first equation, dc1 d2 dt, sorry, this is 2 by the way, yeah, sorry for that. So in the first equation, so this is equation number 1, this is equation number 2. So from 1 we have, now we'll put the value of we'll put the value of r from this equation. So r is rt minus c1 minus c2. So we'll put the value of r here. So this becomes dc1 dt becomes k1 into L into RT minus C1 minus C2. Right. We are just doing to remove R from the equation because we already have we can represent it in terms of RT, C1 and C2. So that's why we are just removing R from the equation. So we are making it in terms of the other parameters. Yeah. So this, the first term becomes this, and the rest of the terms will remain same. Minus K3 C1 minus K2 C1. Sorry, K2 C1. Erase it here. K2 C1. Okay. So for C1 alkyne, C1 alkyne dc1 dt equal to 0. Now you put this thing equal to 0. So this becomes K1 L RT minus C1 minus C2 minus K2 C1 minus K3 C1 equal to 0. Okay, now we need to like rearrange this. So this becomes K1 L RT minus K1 L C1 minus K1 L C2 minus K2 C1 minus K3 C1 equal to 0. Right? Now you take C2 on one side and C1 on another side. So C2 is this one. So K1 L C2 equal to K1 L RT minus K1 L C1 minus K2 C1 minus K3 C1. Right. Now C2 you divide by K1L both side. So this becomes RT minus this. If you take minus 1 minus common, because these three terms contain C1, so minus C1 you take common out of here, and then you divide it by K1 by L, K1L. So this becomes 1. So 1 plus, if you take if you have taken minus C common, so plus K2 K2 plus K3 by K1 into L into C1.
That K2 and K3 should be plus because you took them to out. I mean
Sorry.
that side of equal to na.
No,
I think
I just took this on. Sorry. Yeah, I just took this term on the left. On this side of 0, rest of the terms are there. Only K1 LC2 is taken on the left. Rest of the terms are here.
okay. Okay.
Yeah. So this is a positive one only. So K2 plus K3 by K1L. Right. So I think this is what it is asking. So which one it is, I have to check. So RT minus C1 1 plus K1 plus K2. Yeah, option number C, I think. Yeah, option number C. RT minus 1 plus K2 plus K3 by K1L into C1. That is one. This one. RT minus 1 plus K2 plus K3 by K1L into C1. So this is your null claim. Option 3. I hope this is correct. Yeah, that is the one.
Can you do the calculations?
Yeah. Let's do it. Okay. The question says L binds reversibly to a molecule of R, which gives so basically the rate constant is given forward and reverse. Initial concentration of L and R are given. The concentration of L is much higher than the concentration of the receptor. Therefore, consider free ligand to be constant and also assume the total concentration of the receptor is constant. Okay, what is the steady state? Okay, so what you have is, if R and L is binding to form a complex. Let's call it C. So R plus L, in a reversible way, it is forming the complex. There is a forward rate, there is a backward rate. Both rate values are given. So if you try to model this equation, so dc dt is basically k1 to RL minus k2 into C, right? Now here R is the concentration of the free receptor. So R is concentration. This is not the total concentration. This is concentration of free receptor, right? And the initial concentration, that is the initial total concentration, is given as 0.001, I think, right? 0.001 millimolar. So let's assume the total RT, which was the initial one, this is 0.001, equal to R plus C, the complex formed receptor and the free receptor, right? That is the total receptor, and that was the initial concentration. Okay, now if we rewrite these terms, this is R, sorry, this is R. So if we rewrite this equation in terms of RT, this becomes dc dt equal to k1 into, you replace R by RT minus C, so RT minus C into L minus K2C. Okay, now at steady state dc dt equal to 0, put dc dt equal to 0, and then you put this equation there. So k1 into RT minus C into L minus K2C equal to 0. So your C becomes k1 RT minus, oh no, so C has been taken on that side, so let me write it properly. If you take k1 RT minus k1 CL minus k2C equal to 0. Now you take C on one side, C into k1 L minus k2, sorry, plus k2, both of them on the same side, equal to k1 RT. RTL, sorry, there is a L here. This L I missed here. Yeah, there's an L here. So K1, let me write it here. K1 RTL. So C becomes K1 RTL by K1 L plus K2. Now you'll see all of these equations are given. So we need K1, we need K2, we need RT, and we need L. So let's see what are the values. K1 and K2. So K1 and K2 are given as, I think K1 is 1. I'm not sure what is this value, like it is, if it is 1.1 or not. I think this is 1 only. This is 1 and this is 10. K1 is 1 and K2 is 10, I think. Yeah. K1 is 1, K2 is 10. Now RT,
I think that means per millimole and per second, I think.
1 per millimolar. It is given like, oh, okay. The unit are given like this. Okay. Yeah, it's a little bit confusing. Okay, so L is given as 1000 and R is given as, basically the total concentration of R is given as 0.001. Okay, RT equal to 0.001 and L is given as 1000. Now you put it in the equation. So C equal to K1 is 1, RT is 0.001, L is 1000 by 1 into 1000 plus K2 is 10. So this becomes, so 3 zeros, 1 2 3, so this is 1 on top by 1000 plus 10, so 1 by 1010, so 1 by 1000, so it becomes around this figure, 0.00099. So 0.00099. So this is option number, I think, 1. Yeah. Okay. Yeah. Okay, let's move on to the next one.
Option D, last option.
No, you have to remember this, that I is involved in the production of X. So a constant input signal I induces the production of X. So option D does not have I in it. So it is definitely not the answer. You have to keep two things in mind. One is the I should be involved in the production of X, and X is getting degraded, undergoes first order degradation. These two things. Yes.
See?
C. Yeah, this is the correct option because it is I is involved and this is the first order degradation. So this is incorrect. This is production, and this also is correct, but it does not have I. So option C is the correct option. Okay.
Can you do the qualifications?
Yeah, this is pretty simple actually. So your Km is by definition. So let me write the equation here. Reaction equation. So yeah, your Se is given C and P and E. Okay. This is K1, K2, C, and this is getting degraded K3, P and E. Okay, so this is your equation. Now, by definition, the Km value, the Michaelis Menten constant, which is the Ka, is defined as K1, K2 plus K3 by K1. We actually derived this in one of the tutorial classes if you want to go back and look. So this is actually the definition of Km. K2 plus K2, which is the reversible this, K3 and K1. So this is how we define. Now all K1, K2, K3 values are given. So K1 is 10, K2 is 2 and K3 is 8. K1 is 10, K2 is 2, K3 is 8 and K1 is 10. So this is basically 1. Just a simple formula, nothing else. Okay. Yeah, answer is 1.
Can you do this?
Yeah. So in the first OD, so basically this is a network motif that has been presented, and S is an external signal, XP and YP are phosphorylated X and Y, and total is given by XT and YT, right? Now YP in the first OD, if you look at the second term, it has YP in it. So YP is positively regulating the production of XP. If you see this, so YP, this is a positive symbol. K3 into YP, what it means is YP is positively regulating signal of XP. So this is good. In the first equation, YP is positively regulating XP, right? In the second equation, if you look in the first term as well, sorry, yeah, if in the second equation also, if you look in the first term, this it has XP in it, and this is dyp dt. XP is also positively regulating YP because this is a positive term here. So on the one hand, in dxp dt, YP is positively regulating XP. In dyp dt, XP is positively regulating YP, right? So, and there is no other cross regulation in both of the equations. In XP, only this term contains Y. In dyp dt, only this term contains X. So there is no other cross regulation. In this first equation, YP is positively regulating XP. In the second equation, XP is positively regulating YP. So this is basically a positive feedback loop, right? So because YP is positively regulating XP, XP on the other hand is again positively regulating YP. So this is a positive feedback loop. So this is option number 3. Understood?
Yes.
Okay.
What is mean by adaptive motif?
Adaptive motive is basically when one of basically one variable, the steady state of one variable is independent of the other. So basically this will be an adaptive motive when the steady state value of Y is independent of S. That is an adaptive motive. So basically, even if you change the value of if you change the steady state of S, the y steady state will not change. The y steady state is not dependent on the value of s. So if you slightly change one of the dependent variables, the steady state of the other dependent variable does not change. So this is the concept of adaptive motive. Ki, like if you change the signal of one of them, the other ones does not get affected, or it remains to stay in that steady state. So that is how we define an adaptive motive.
Okay.
Basically, the approach is simple. You need to find the steady states of both and see if basically x or y depends on s or not.
Can you tell the answer?
Yeah, actually, you need to check it for all the options, but I think the correct option is option 1. So we'll check it for option 1 only. Just let me write it here. The same way you can check it for the other options as well. So your equation is, so k1s minus k2x. Dx dt equal to k1s minus k2x, and dy dt equal to k3s minus k4xy. dy dt equal to k3s minus k4. Let's write it like this. xy. Okay. Now at steady state both of them equal to 0. So first let's do dx dt equal to 0, which brings k1s equal to k2x. So x becomes k1 by k2 into s. Right. Now you check the steady state of y, dy dt equal to 0. So k3s minus k4xy equal to 0. Now in place of x you put this value. So 0 equal to K3S minus K4 into K1 by K2 S into Y, right? So Y, so this is basically K1 K4 this K2, sorry, by K2 into Y into S equal to K3S, right? Now S is non-zero, so this gets cancelled out. So basically the steady state value of Y does not depend on S, the input signal. So steady state of Y does not depend on the input signal, which is S. Hence, it is an adaptive motive. Okay. Okay, I think that's all. That's all the questions that I had. So yeah, time is also up by 15-20 minutes, but okay, that's not a problem. But I think I hope this session, like, at least helped you do some revision and stuff for the exam. You have the exam next week, so best of luck for the exam. And yeah, sorry, stop presenting, cancel. Yeah, so yeah, if you face any issues from now till the exam related to exam, if it is urgent, do send me, I'll look into it. The other one that you sent, I'm going to need some time to look into it carefully. But anything related to the exam, you can also send to me if you find any issues. And yeah, that's all from my side today.
Okay. If possible, can you share your number? I mean, WhatsApp number or something, contact number,
Okay.
if possible.
I'll not share it here, I'll share it in the mail. Yeah, okay, because this is
Okay.
getting recorded, this will be on YouTube also. Okay,
Okay.
I'll share it in the mail. Okay.
Okay. Thank you so much for the revision.
Yeah. Yeah. Thank you for joining, and best of luck for the exam. And yeah, thank you. I'm going to close this session. Yeah.
Okay. Bye.
Bye bye. Thank you.